So for today, it is probability and using tables. So by the end of the hour, you will know some more probability terms, things that I guarantee you don't know right this second, like fancy names for some of the terms we use. And the difference between experimental and theoretical probability and how to use contingency tables. So here we go. Let's talk about some vocab. Random. All right, if I toss a card into the crowd, there, it goes closest to you. Was that truly random? No, because I tossed it in a direction. You know what I mean? That wasn't equally likely to land over there or over here. There was a little bit of randomness, but I was probably going to hit, one of 3 or 4 people. So that's not random. So you have to make sure that no individual outcome is predictable. And I would say it this way. No outcome is more likely, than the other. So anyway, you have to make sure you're doing things randomly when you're doing probability. All right. If you roll a die, is it truly random? Well, as long as there's not something funky going on, like weighted dice or whatever, then this is equally likely to come up with a 1, 2, 3, 4, 5, or 6. But what if I was suspicious? Would you agree that if I rolled a die and it came up 6 5 times in a row, I might be suspicious that something weird's happening? You get a whole bunch of the same number. Well, then you could do what is called experiment. You could take an experiment and do that. Would rolling the die 3 times be a good experiment? No. Would rolling it 1,000 times be a good experiment? Yeah, then all of a sudden, if after 1,000 times you were getting 900 sixes out of 1,000, you'd be like, that thing is broken, because you did experimental probability to verify the theoretical, what it should be. Shouldn't a die come up 1 out of 6 times? The number you want? Shouldn't it be 1 out of 6? Yeah, and if you actually do an experiment with only 6 trials, the outcome, fancy name for rolling a die, was the event. The outcome, coming out either heads or tails, that outcome, was it random? Well, I'd be suspicious if I wasn't getting similar equal numbers of heads and tails, or on a die, if that's the event. If it isn't coming up kind of an equal number for each of them, I'd be suspicious. All right. This is one that I bet you've never heard of before, the sample space. What that is a list of all the things that could happen. So when you're rolling a die, what's the things that could happen? 1, 2, 3, 4, 5, 6. It is only 6 sides. Well, there can be 7-sided dice. There is such a thing. But most dice that you see are 6-sided. How about flipping a coin? What's the sample space? Heads, tails. It's just a list of everything that could happen. Does that make sense to you? All right, I'm going to give you a different definition of probability. It's what you want over what is possible. I think that you will come back to this over and over again. Technically, here's the rest of the definition. Wanted outcomes. But all of a sudden, now my brain is saying, I don't know what that means. It's what you want over what's possible. Possible outcomes. Let's do it in the context of dice. Do you get that if you're going to do a die, you've picked a number. How many numbers do you get? Well, you just get 1. Then what's your wanted outcome? Let's say I want it to be a 6. Then would I put 6 on top? Nope, because there isn't 6 things that could happen. How many things do I want to happen? 1. Out of how many possible things are there? 6. So it's what you want over what's possible. All right, let's talk about it in a different context. Let's talk about cards. I know some of you are experts at cards, play them all the time. Anybody in here actually enjoy playing cards with their buddies? You play poker together or anything? A few of you, okay. And this is a deck of cards. It just happens to be gold, just to make it more fun. There's a process by which you can make gold stick to things. And this is gold leaf, it's called. So, if I shuffle it up, I'm not doing a card trick here. I'm truly just kind of shuffling it up. I do not know what card came onto the top, but it turned out to be a 5 of spades. What was the probability of that? How many 5 of spades are there in the deck? Only one. Now, I know some of you don't know what the deck of cards is. I have another slide where I show all the things. But there's only one in there out of, do you know how many cards are in a deck? 52. Then it's what you want, which was that I want to know about the 5 of spades, and there was only one of them. One of the things I wanted out of what was possible, 52 things were possible. We'll do more with the cards in a minute. So I just wanted to give you my definition of probability. It's what you want over what's possible. We'll come back to that. Now, probabilities are a decimal because why? Because you could divide them. Let's say that your probability came out to 4 out of 12. Would you agree that's the same as 1 out of 3? And would you agree that that's 0.33333? And it keeps on going forever. So then my probability, at some point you have to stop writing 3s. Let's say they want 2 decimal places. A lot of times on our tests, we want 3 decimal places. Then I guess we would go out to here. Then that's how you'd write your probability. Do you think you'll ever get anything higher than 1? No, think about it. If the probability is 1, it's 100%. It's like 10 out of 10. There's 10 red marbles in the bag and nothing else. What's the probability you're going to get a red marble? Well, there's 10 and I want 10. There's 10 and there's 10 possible. 10 out of 10. 1.0. So 1 is the highest probability there is. And zeros in the real world, there's not many things that couldn't happen. Is it possible that a giant pink elephant could break into this room and rampage until it squashes Moreno? Is it possible?
I mean, if you want to get really deep into this simulation.
Okay, all right. So I know some of you are like, okay, what's the probability that Mr. Server has arranged for the door to open and somebody in an elephant suit to run in the room? So there is a close to 0 probability chance that that's going to happen. All right. So I would just say that 0 is really unlikely, and 1 is also very unlikely. Like if I say the sun will rise tomorrow in the morning, is there a chance that it won't? Yeah. Now, if it doesn't, we're all toast. Because, yeah, it's true. The light from the sun is 8 minutes old, so if the sun exploded a few minutes ago, we wouldn't know yet. Kind of crazy to think about. All right, let's move on. This is one of the most misunderstood probabilities in math, and that's when you make 2 dice go together. Do you get some people think the probability of getting a 7 and getting 6 are like equally likely? They are not. Let's investigate why. Do you get that there are 6 things that I've got 2 dice here, and I'll make it really clear. I'll make one of them white and one of them blue to make it really clear distinction between the two. We got a darker one and a lighter one on here. Do you get, if I roll these 2 dice, there are 6 things that could happen on this one, and there's 6 things that could happen on this one, and I'm going to tell you something that really comes in handy in the advanced probability. Always multiply your choices. I got 6 choices of things that could come up here and 6 choices that come up here, and if I multiply them, that means there's 36 things that can happen, and here is a list of all of them. 36 things can happen. How many of those things make up snake eyes? Only one. This is one event. The darker dice came up a 1, and so did the lighter dice. It came up a 1. There's only 1 in 36 chance of that happening. Do you get, if you're betting on snake eyes, it's not likely. In fact, there's a 1 in 36 chance that you're going to get snake eyes. And I know some people are like, can't you reverse the 2 dice? Nope. That'd be something like this. the dark die could be a 1 and the light die could be a 2, or it could be backwards. That is 2 in 36 chance of happening. So let's say you wanted to con your little brother and you say, let's play a game. And if it comes up 7, I win. And I'm going to give you 2 and 3. Is there an equal chance that you're going to win? No. With the 7, you got an advantage. What if you say, I'll give you 2, 3, and 4? If any of those come up, you win. And the only way I win is if 7 comes up. Do you get how you could probably con some people into that deal? Because they got 3 numbers and you only get 1. But yet, with a 7, that's the most likely number, of course. Then that is the things that make you win. And there's 1, 2, 3, 4, 5, 6 of them. So you have 6 out of 36 chance that you're going to win. And if your little brother has all of these, well, then actually your little brother would have an equal chance as you then. So if you got out of control and said, little brother, you can have 2, 3, 4, or 5. Now your little brother's going to win in the long run. Do you get if I just do it once, though? I mean, it can't really tell from just once who's going to win. But if I do this a whole bunch of times, the little brother would now have 4, 5, 6, 7, 8, 9, 10. They have 10 ways to win. You only got 6 ways to win. They're actually much more likely to win now. All right. The magic of Las Vegas is to set up situations where people think that they have a fair chance of winning, but they really don't. And so the magic of Las Vegas would be to say, I'm going to set it up in such a complicated way that you think you have a 50-50 chance, but you really don't. And all this house has is like a 2% advantage. But if you keep doing that over and over and over again, the house is going to win, meaning the casino is going to win.
And then if you card count, they just kick you out.
That's true. If you want to get an advantage by counting cards, there's good movies about this. It is not illegal to count cards, but they also have the right to refuse to let anybody play. So if they decide, we don't want you playing, they can kick you out. So if you count cards and you tell them you're counting cards, that's kind of dumb because they're just going to walk over and say, sorry, you got to go. Now, some people are so bad at counting cards that they're just going to let them play because they think that they have an advantage, but they don't because they're not good at it. So they might even see somebody counting cards and be like, yeah, and he's doing it wrong. So we're just going to let him play because he's probably thinks he's got an advantage and he's going to bet all kinds of money, he's going to lose it. So, but there have been some stories of people that have actually found ways to like be really good at it, and then they have to get into crazy things like disguises to try to hide the fact that, like once they have their face, then they use face recognition software in the casinos to go, oop, there's that guy that knows how to count cards. Don't let him play. You know what I mean? And so then they start wearing disguises to try to throw out the face recognition. Anyway, so it's all about knowing the math. And if you know the math, there is actually one bet in Las Vegas, and that is just fair. And it's complicated. It's not something simple like roulette is fair. Nope, roulette is totally not fair. But there's one bet in Las Vegas that is, and all you can do is get a fair bet. And that's where you have a 50-50 chance. It's kind of like betting on the coin flip and actually getting fair odds. You have a 50-50 chance and they'll pay off exactly fairly, and that means you don't have an advantage. It just means that you're equal. It'd be kind of like saying 1, 2, 3, 4, 5, 6, 7. These, you get these, and I get the 7 and a 1. Because then you have equal chances as me. There's only one bet in the whole city of Las Vegas that is fair, where you have 1, 2, 3, 4, 5, 6, 7 things, and they have 7 things, and it's in the game of craps, and that's the one where you have dice. You roll 2 dice, and it's a complicated bet even to explain to people. So it's obviously they don't want you to have fair bets. Every other thing there is in their advantage, and so, but they can't have it hugely in their advantage, because if you're in a casino and everybody's losing, nobody would be having fun. Like, people aren't stupid. Well, they might be a little bit stupid, but they're not super stupid. And so if everybody lost every time they went, nobody go to casinos. They have to make it so you win sometimes. And that they just have a small advantage. And that way you'll keep going. All right, here's that deck of cards. Let me give you this advice. It's what you want over what's possible. Can you figure out the probability of getting a black 7? How many are there that you want? 2 out of how many are possible? 52. There's your answer. Now on today's, I'm fine with you leaving it as a fraction. It's also a decimal. Do you get I could divide these two and get a decimal for that? On the test, you will have to give me decimals. Today, I don't want you to have to get out a calculator and just divide them all. It would just be 2 divided by 52, okay? But if I wanted to get this to be out of 100, it'd actually kind of complicated because it's out of 52, so it's not going to like be a nice simple conversion. So you can leave them as fractions. All right, here's another one. See if you can get what you want goes on the top. Given I sort the deck down to just the hearts, what's the probability then that I pull the 10? Given I'm only picking hearts, what's the probability of the 10? Ask the kid next to you and see if you get the same thing. Do you get if it's only the hearts, it's out of 13? If maybe you haven't played cards enough to know that, or maybe it's hard to do 52 divided by 4 in your head, but it's 13 possible. How many 10s are there? 10? Did I put a 10 on top because I wanted the 10? No, how many 10s are there? 1. Because only hearts is the only thing we can pick from. So it's out of this, and it's that, so it's 1 out of 13. Who had 1 out of 13? Okay, good. All right, move on. Experimental is where you like actually do an experiment. So imagine this is a deck of cards. Do you know for sure that it is a complete deck of cards? No, I could have totally stacked this deck. It could be 2 decks I mixed together. It could be less than a whole deck. So you don't know. So what if we did an experiment and I had 10 kids grab a card? And what if all of them got an ace of hearts? Would you be suspicious? Yes. So then that would be doing an experiment. And it doesn't always come out like the deck of cards should have 52 cards. You have a 1 in 52 chance. Well, if you do an experiment, sometimes you realize that the theory is off because the actual things are not what you expect. All right, so an experiment is where you do it in the real world and the numbers don't come out like you expect. Here's one more example. Theoretically, you flip a coin, isn't it a 50-50 chance that you're going to get a heads or tails on a typical coin? Yes. So you got a probability of 1/2 that you're going to get a heads. Do you get that that's theoretical, though? If I actually flip a coin 2 times, shouldn't it come up heads once and tails once? But do you get there's actually a fairly strong probability that it won't do that? Okay, so then that's where you do an experiment. So if you do a small experiment, it's risky because if you only flip a coin twice and it comes up tails, you haven't really proven anything. But if you do 1,000 flips and it comes up 500 heads and 500 tails, do you get that? Probably verifies the experiment verified the theoretical. But you have to do enough of them to make it work. Okay, enough about that. The next thing is called a contingency table. These are more fun if you actually do them like where you pick in the room. And so I'm going to make one of these in a minute, but for right now, we'll just use this one. Let's say that we had 100 people and we asked them, and they were only freshmen or sophomores, and they were either right or left-handed. In this room, in a second, I'm going to ask you that same question. Freshman, sophomore, or junior, or left or right-handed. Then I'm afraid my juniors are going to be like, oh, I'm the only junior in the room. I don't want to, so I don't want to make you feel bad. So I think I'm going to change it to pets and left or right-handed, because I think most of you don't care if everybody knows that you have a cat and that you're left-handed or whatever. Okay, so back to these numbers. How many people were polled? 100. How many were freshmen? Is it 43? No, 52. How many of them were left-handed? You go down here to get the total, 13, good. How many were sophomores? You look for the total. How many were right-handed? 87. Okay, now here's where they get more complicated. How many people were sophomore and left-handed? Sophomores and left-handed, that would be 4. So then do you get, if I asked you for the probability that we grab a random person and get a sophomore who's left-handed, oh, it gets complicated. Then it's 4 out of 100. Freshman and right-handed? Freshman and right-handed. 43. Out of what? Well, if we pick out of everybody, it's going to be out of 100. But wait, listen, this is important. What if I change the question to, given I only talk to right-handed people, what's the probability that I get a freshman? Mr. M, could you go get a drink? It'll help. Go get a drink. It's good for you. All right. So what's the probability that if I only talk to right-handed people, that I get a freshman? 43 out of 87. Raise your hand if you knew what I was talking about. Okay, good. Do you get it's out of 87 all of a sudden? That freaks some people out. Why is it out of 87? Because I said we were going to only talk to right-handed people. All right, so now we got to do one more like that, except I'm going to make up righties and lefties. You guys all know if you're a righty or if you're a lefty. In theory, I could add a third category for truly ambidextrous. Is anybody in here going to make an ambidextrous claim, like you actually can do both? A little bit. So I can say a little bit too, like I can do left-handed hockey and I can do right-handed hockey just about as well. But let me ask you this question. If I was going to judge your left-handed writing and your right-handed writing, would they be about the same? Okay. All right. Because writing is kind of the true test. All right. So we're just going to have only right and left-handed. But then I'm going to have dog, cat. But as soon as I add dog and cat, what's the other possibility? Both of them or none. As in you don't have a dog or a cat. Maybe you've got a gerbil, but you don't have a dog or a cat. All right, you belong in one of these boxes. So I'm going to ask for each box to raise your hand if you are in this box. If you are a righty and have a dog, you'd be in this box. Who's in that box? Right-handed and have a dog. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Who is lefty and has a dog? All right, 1. Who is right-handed and has a cat? 1, 2, 3, 4, 5. Who is right-handed and has both a dog and a cat? 1, 2, 3 of you. Who is right-handed but does not have a dog or a cat? 1, 2, 3, 4 of you. Okay. Who is a lefty and has a cat? All right. Who is a lefty and has both a dog and a cat? All right. And who is a lefty and does not have a dog or a cat? Neither one. Okay. So we only have one lefty in the room. So now this is the part where you make totals. Total up every category, both on the right side and on the left side, and then the grand total, which is probably the most used number of all. And it's kind of cool because it adds up in both directions and it works out, if I did it right, to be 24 in both directions. I think I did it right. Did you guys get the same numbers as me? Okay. All right, now I'm going to ask you a typical harder probability question. So if I had only the cat owners stay behind, what's the probability it would be a righty? 5 out of 5. Yep, 100%. Okay, so it's going to get more complicated. I'm going to write this down. What's the probability that I get out of a random group of you, this whole group out of all of you, what's the probability I grab a left-handed dog owner, or I get a right-handed cat owner? Now, when they get complicated, go back to it's what you want. How many things are there that you want out of what was possible? And remember, I said I was picking from everyone. All right, total it up. Get an answer, simplify it if you can, and then talk to the kid next to you on what you think that answer is. Okay, so there's what I meant and then there's what I said, and they can be different. And I would have to be clear on this on a test. I would have had to accept both answers here. Would you agree that left-handed dog owners, there was only one possible? Out of, how many people were we picking out of? 24. But the answer isn't one number 24, obviously, because we also want to include this. Next thing I want to tell you is that or usually means add. We're going to add in the right-handed cat owners. But somebody made a really good point. The right-handed cat owners, there were 5 of them. But aren't these also right-handed cat owners? I know it's kind of tricky, but those people have both a dog and a cat. And they're right-handed. So aren't they also right-handed cat owners? Yeah, now I know I would have had to accept that answer as oh, also these guys. But I wasn't super clear on whether I meant only have a cat versus they have a cat. Because there's a difference. If I said they only had a cat, then I should have just picked the 5. But these people have a cat too, so that made it more complicated. I would have had to either accept 6 out of 24 or 9 out of 24. Both of them would have been good answers on the test. Okay, I think you understand what is called a contingency table. And by the way, what the heck is a contingency? A contingency is where you say, contingent upon only talking to lefties. Do you get how I just narrowed my table down to just that? So a contingency narrows your table down to just part of it. If I only talk to lefties, what's the probability I get a freshman? 9 out of 13. Whereas if I had just said, what's the probability of a left-handed freshman? 9 out of 100. So it depends. Did you narrow it down to only? That's called a contingent. Contingent upon the person being left-handed, that means you're only going to pick these people. Then it would have been 9 out of 13. Okay, good enough on that. Your homework has a small number of problems, but there's like A, B, C, D, E on a lot of the problems. So what we're going to do is skip problem number 2, which actually skips 6 problems. Because it's got 2A, 2B, 2C, Z, E, F. Okay, so we're skipping number 2. And I honestly think that you will finish it during class. It should be something that's kind of like mildly fun and fairly easy. Don't have to divide them and get decimals. That's part of what makes it save it a lot of time. I'm not going to make you give me the decimals for them. If you want to, you can. But basically skip number 2, do the rest, and I think you'll find this pleasant. And that's all I got for you for today.